Welcome to The Explainer. Today, we're going to be diving into a really special class of systems. Systems that are, believe it or not, perfectly predictable. Honestly, they're the bedrock of modern signal processing, and getting a handle on them is kind of like having a superpower for prediction. So, let me just start by posing a question. Think about a complex system, maybe an electronic filter, an audio equalizer, or even a control system for a robot. How on earth could you know exactly what it's going to do to any signal you put into it? I mean, it seems impossible, right? Okay, so before we go any further, let's get on the same page. What even is a system? Well, you can just think of it as a black box, a process that takes something in, we call that the input signal, and spits something else out, the output signal. A microphone is a perfect everyday example. Sound waves go in, and a totally different thing, an electrical signal, comes out. Now, the answer to our big prediction problem isn't trying to test every single possible input. No way. The secret, the real trick, is to focus on a very special but really common type of system, the linear time invariant system, or, as we'll be calling it, LTI for short. And the core idea here is it's brilliantly simple. To figure out how an LTI system will react to a really complex signal, we first have to break that signal down into its simplest possible pieces. You know, it's almost like taking a big Lego castle and disassembling it back into a pile of individual little bricks. So take a look at this. Up top, we've got a typical digital signal. We're calling it X of n. It's really just a series of values, or amplitudes, at different moments in time, all stuck together to make this one complicated-looking shape. But here's the real magic, the big insight. We don't have to see this as one big, messy shape. That equation you see there, it's showing us that we can think of this entire signal as just the sum of all its individual pieces. We're going to deconstruct it. So what's the simplest possible piece? What's our universal Lego brick? It's this little guy right here, the unit impulse. We call it delta of n. And it's nothing more than a single, instantaneous blip. It has value of 1 right at time 0, and it's 0 literally everywhere else. That's it. That's our universal building block. And this leads us to the most important question of all. If we know that any signal is just a collection of these simple impulses, what happens if we test our system with just one of them? What does the system spit out when we feed it the absolute simplest thing we can? Well, the output we get is something special. It's called the impulse response, and we label it h of n. When our little impulse, our delta of n, goes into the LTI system, this h of n is what comes out. And you have to understand, this response is the key to everything. It is the system's unique DNA, its fingerprint. Now, this fingerprint is only useful because LTI systems play by two very strict, very predictable rules. These are the L and the TI in LTI. Linearity and time invariance. Let's break down what these actually mean. Okay, time invariance is pretty straightforward. It just means that if you shift the input in time, you get the exact same output, just shifted by the same amount. So if you clap your hands into a microphone at noon and get a certain sound wave, clapping the same way at midnight will give you the exact same sound wave, just, at midnight. The system's basic behavior doesn't change over time. Linearity is all about scaling and adding. It means two things. One, if you double the input's strength, you get double the output strength. And two, if you add two different inputs together and send them through, the output you get is just the sum of what you would have gotten from each one individually. This property is absolutely crucial. It's what lets us break signals apart and then add the results back together. So, let's put it all together. We have the system's unique fingerprint, the impulse response. And we have two incredibly powerful rules, linearity and time invariance. With just those things, we can predict the output for absolutely any input signal we could ever dream of. And the mathematical process that lets us do this magical process, is called convolution. Now, I know that word can sound a little intimidating, a bit heavy on the math, but conceptually, it's really just a systematic, step-by-step way of applying that fingerprint to every single point of our input signal to build the final output piece by piece. In fact, let's just forget the scary equations for a minute and see how this actually works visually. We can really get a feel for convolution with 4 simple steps: flip, shift, multiply, and sum. All right, step 1. We take our impulse response, that system fingerprint, h of n. The very first thing we do is just flip it. We reverse it backward in time, creating a mirror image of it. This is just getting it ready to slide across our input signal. Now for the fun part. We take that flipped fingerprint and we slide it so it just lines up with the very beginning of our input signal. Then we multiply the values where they overlap. In this case, it's just one spot. And we add up the results. And boom, we get 0.5. That is our very first output point. What's next? You guessed it. We just do it again. We slide that fingerprint one more step to the right. We multiply where the signals overlap now, and we sum those products. This time we get 2.5, and that becomes our second output point. You see the pattern emerging here? And we just keep going. We just keep sliding, multiplying, and summing step by step all the way across the entire input signal. Each one of those steps generates one more point of our final output until we've built the complete response from scratch. And just like that, we've done it. We took one simple test result, that impulse response, and used this methodical process to perfectly predict how the system would behave with a much more complex input. That right there is the awesome power of convolution. And look, this isn't just a neat little trick. This is a fundamental principle of signal processing. As the source material puts it so well, the characteristics of an LTI system are completely determined by its impulse response. Everything you could ever want to know about the system is encoded in that one simple signal. And when I say everything, I mean everything. Just by looking at the shape of that fingerprint, we can diagnose the system. We can tell if it's causal, which basically means, does it obey the laws of physics and not react to something before it happens? We can tell if it's stable. Is it going to behave, or will a normal input cause the output to fly off to infinity? We can even tell if it has memory, or if it only reacts to what's happening right now. All of that just from looking at one signal. So why does any of this matter in the real world? Well, because LTI systems are everywhere. They're fantastic models for audio filters, for control systems in cars and airplanes, for communication channels, you name it. This entire framework is what allows engineers to analyze really complex systems, and more importantly, to design new ones that have perfectly predictable behavior. So we've seen just how predictable and powerful these LTI systems are, and it's all thanks to that simple fingerprint. But this leaves us with one final, pretty fascinating thought. If these are the predictable machines, what kind of secrets and complexities are waiting for us out there in the systems that don't follow these simple rules?